we'll start with moment distribution method of analyzing the same plane frames. So before going for the actual analysis of moment distribution, let us spend some time on the basic fundamental chapters which has been already studied in slope deflection equation, that is stiffness and carryover factor. So the definition of stiffness and carryover factor, that let us define first. After understanding this stiffness and carryover factor, then we can go for this moment distribution. Already a notes has been circulated to you. There I have defined what is meant by stiffness of a prismatic plane framed structural member. I defined this structure, the stiffness of a plane framed structural member as the force developed due to unit displacement. That means, in the case of plane frame structural member, the possible displacements are shear and rotation at the two ends, either by giving a unit rotation or by giving a unit translation, or either on left end or right end of the member. Unit displacement or translation, what is that force required to give that displacement? We call it as the stiffness. So that means first we assume both ends of the member restrained, there is no displacement at all. Then we force one end of the member, we give a rotation equal to unity in the positive direction, like this. Let us force this left end in the clockwise direction and give a unit rotation like this. Then, since it was fixed, we are forcing that particular end to give this unit rotation. When we are forcing to give this unit rotation, there must be a force required to cause this displacement. And that force, we call it as the stiffness. So you can prove that force as 4A by L by energy principle. That is strain energy method, that is Castiglione's theorem. You can apply and derive this, which has been done in the previous year. So I don't want to go into the detail of the derivation. Just remember the force required to give a unit rotation either at left end or right end, because we are worried about only the joints, displacement or the forces developed at joints of the structures only. So we give displacement at one end of the joint, whatever the force required to give that particular displacement, we call it as the stiffness. This we define as the stiffness. The other end will be fixed only. When we force this end and give by this force, there will be a unit displacement at this end. Then when we are forcing, since the other end is also fixed, there will be a reaction from the other end, because the member AB altogether put together, it will act to resist that particular force, or it will resist that particular displacement. And the force developed on account of this is half this particular value at the other joint, and that value will be equal to 2EI by L, where EI is the flexural rigidity of the member and L is the length of the member. And this force which is going to develop in causing this unit displacement by this force, we call it as the carryover factor. Carryover factor, because we are giving unit displacement here by this force, it will have an effect at the other end. So this force will be carried equal to half its value to the other end also, and this is called carryover factor. Same thing will happen here also. At this end, if you give unit displacement with this end fixed, the force required at that end will be 4EA by L like this. If you rotate this end by unity, this end being fixed, here the force will be same value 4EA by L because it is same member, same EI, same L, that same force will be developed, and here also there will be half this particular value is going to develop at the other end. So this particular aspect has already been used in the slope deflection method also by giving a rotation theta A at one end. So the force developed at that end will be 4A by L into theta A, because this is for unit rotation. If you have a rotation of theta A, force developed due to that rotation will be 4A by L into theta A. Similarly, when a force, when a displacement is given at the other end by theta B, force developed at this end will be 2EA by L into theta B. So similarly, translation, if we take and add all these, we get that slope deflection equation, moment developed at that end. That is exactly the derivation of that slope deflection equation from the stiffness. Because this slope deflection equation, moment distribution method, they are all same displacement type of method of analyzing the structure. Same principle is being used. Similarly, a translation, if you give a translation at one end by unit translation here. Earlier it was fixed at both the ends. Now I am forcing it to move in the vertical direction by unity. The force required to give that can be derived as 12A by L cube. Now this, in all these cases, this element or member has to be in equilibrium. See now here, 4A by L will be here, 2A by L will be here. This will not be in equilibrium because this keeps on rotating. To keep this in equilibrium, there must be a equal and opposite moment developed by two equal and opposite reactions, because these reactions can be developed. This reaction also will be developed automatically. The moment you give a unit rotation at one end, all these forces, four forces will come into picture. This value will be 4A by L, here it will be 2A by L, and this value, it will be 6A by L square. How you get this means, this is 4A by L, this is 2A by L. So this, suppose if I call some reaction B, if I take moment about this point, V into L is equal to 4A by L plus 2A by L, that is 6A by L. Therefore, this V will be 6A by L divided by L, that is 6A by L square. When this is here, then this is again imbalance. Sigma V has to be 0. So here it should be equal and opposite. So this will be also 6CI by L square. Now these two are parallel forces which are equal and opposite. So they give a moment in the other direction which will oppose this. Now this is perfectly in equilibrium. So when I give a unit displacement like this, there will be a force of 4A by L at that end, there will be a force of 2A by L at the other end, there will be two reactions, 6A by L square. Same kind of thing here also. Here it will be 6, because this is clockwise, this has to be anti-clockwise, so there must be force here like this, force here like that. See, this and this, they are similar. 4A by L, 2A by L, and 6A by L square. Here also. Now, when I give a translation, then the force required will be 12A by L cube. This also can be derived by energy principles. As I told you, this can be derived by energy principle. So now, this force will not keep this in equilibrium. If this force is simply acting, it will keep on moving in that direction. So it will not be in equilibrium. So there must, to keep it in equilibrium, there must be equal and opposite reaction here. That this is also 12A by L cube. Again, with these two only, it is not in equilibrium because these two are equal and opposite parallel forces. This keeps on rotating this particular element. It keeps on rotating. To keep it in equilibrium, there must be equal and opposite reactions. That will be like this. So now this is in equilibrium and this value will be 6 EI by L square again. Here moment will be 6 EI by L square, whereas here reaction will be 6 EI by L square. How do you get this? Here total moment, this 12 EI by L cube, two forces, equal and opposite parallel forces separated by a distance N, it gives a moment 12 EI by L cube into L. Because lever arm is L. So 12 EI by L square, that is the moment. Here the two moments has to be there. It should be half. The total moment has to be 12 EI by L square. Half that value will be here, half that value will be there. So this particular development of forces due to unit displacements, we call it as the stiffness of any member. Stiffness of a member due to unit rotation will be 4A by L. Stiffness of a member due to unit translation, it is 12A by L cube, and the corresponding moments developed will be 6A by L square. Here the corresponding moment at the other end developed will be 2A by L. This particular concept you should know. So in the nutshell, the force displacement relationship, we can say force is proportional to D or vice versa. D is proportional to P, because within the elastic domain or elastic limit, you know always the force displacement relationship or stress strain relationship will always be linear. That is, direct proportionality will be there between stress to strain or force to displacement. When it is this relationship exists, you can call this as P equals some constant into D, or this you can say some constant F into P. This constant of proportionality, we call it as stiffness. Here it is called as flexibility, because all members we say it is stiff or it is flexible. That means it is that resistance or inherent resistance of that particular member, that capacity of the member to resist, inherent capacity to resist. This is the fundamental property of any member. So this is by just fundamental basic principles we are defining this stiffness and flexibility. Knowing this, we can define what is stiffness. See, in this relationship, if D is equal to 1, if D is equal to 1 displacement, then K will be P. That means the stiffness is the force developed on account of unit displacement. That's what I have done here. Similarly, here, if P is equal to 1, then F is equal to D. That is, this flexibility is defined as the displacement produced on account of unit force. It is just reciprocal to this. One is reciprocal of the other, flexibility and stiffness. This is actual definition in loose terms. So stiffness is nothing but force due to unit displacement. Flexibility is displacement due to unit force. So that I have derived with reference to expressions, with reference to its geometrical properties like I, L, material property, I define this K. This is a very loose definition of PAD. This is exactly mathematical expression of stiffness of a particular stiffness and carry-over factor. Of course, this already I have circulated as a note. So this is the basic principle of all this displacement method of structural analysis, indeterminate structural analysis. This is exactly what we do in slope deflection also. By deriving the slope deflection equation, we use this stiffness. So this, in the moment distribution method, indirectly we use this as we define stiffness for each member, and that we use rather than slope deflection equation. That's the basic difference between that slope deflection and moment distribution. Same terminology we use, stiffness and carry-over factor only we use, but in a different fashion. There in the form of equation we use in slope deflection method, here we use in the form of basic definition itself. This is one thing you have to remember. Then another basic concept which you have to remember in moment distribution is what is known as distribution factor. Distribution factor, DF. This is another terminology which one has to bear it in mind before going for the moment distribution procedure. Still, after knowing stiffness and carry-over factor, this is another distribution factor. Actually, as the name itself indicates, it is the question of distribution of forces here. Not displacement, distribution of forces among various members. Suppose when this distribution comes into picture, it comes into picture when a particular joint has more than one member at a particular point. So suppose if you consider a joint wherein three members are meeting, right? One is say OA member, another OB member, another say OC member, having moment of inertia I1, length L1, here I2, L2, I3, L3. So then suppose a moment is applied at joint, then that moment M applied at that joint or coming at that particular joint will be shared by these three members. How it is shared? That will be shared in proportion to distribution factor. Is it clear? The distribution factor is nothing but a term which determines the proportion by which a moment at a joint will be shared by a member. If M is the moment applied, then if distribution factor of the member is say some value K, then K into M will be the force which will be taken by this. Or not all M will be taken by this. But displacement, of course, whatever displacement comes at the joint, the displacement at that end of all the members, it will be same, because that is what compatibility condition says. Whatever displacement will be there at any joint, same displacement will be there at the ends of all members. That is compatibility condition, but not the force. If a displacement force is there at a member end, then the force OA, M will be not M, it will be MOA. Here MOB, here MOC. That you have seen in slope deflection equations or method also. While applying equilibrium condition at any joint, intermediate joint, wherein more than one member is there, you are applying equilibrium condition, that sum of the moments of all the member ends will be zero you are taking. And also at an end where it is fixed, where only one member is there, you are not applying any equilibrium condition, that because the moment which comes at that end will be absorbed at that particular joint itself. It will be taken by that joint. It is fixed joint. But if it is hinged joint, then whatever that moment comes at that joint, that has to be thrown to the other members. It cannot take it. That's why there we will say distribution factor is 1. That entire moment coming, it has to be thrown to the other members coming at the joint. This cannot take at all. Whereas the moment coming at this end, it need not go to these members. It will be absorbing there itself. But the moment coming at a continuous joint, it will be shared by these distribution factors. This is another important basic concept which one has to bear it in mind while doing the moment distribution. Because it says moment distribution. Why we are taking moment distribution, not shear distribution means because we assume moments at the ends of the members only as the unknown forces, which we have to determine during analysis. That I told you in slope deflection method. The shear we determine just after determining this moment. To start with, for doing the analysis by slope deflection or by moment distribution or any other method, we select only the end moments. Though there are 4 forces, only 2 we select as the unknown for determining during analysis. Other 2 we determine by equations of equilibrium. Because the moment you know the 2 moments, then if I take moment about this point, this can be evaluated. If I take moment about this point, this can be evaluated. These need not be selected as the unknown. Unknowns can be selected as only moments. When we are taking only the moments, the distribution of moment coming at any joint and how it will be shared by the other members, we should know that's called the distribution factor. And that distribution factor we define as the, suppose distribution factor for this member OA and the joint O, we define as stiffness of member OA divided by stiffness of all members meeting at that joint. All members. This is how we define distribution factor. The stiffness of member OA, this OA, it is fixed at one end, continuous at the other end, it is 4A by L. Continuous at the other end or fixed at the other end. It is similar to this, it is 4A by L. Here also it is 4Al to L2. Here, when the other end happens to be hinged, that point I missed to tell, if the other far end is hinged or simply supported or a roller. If you force this end and give a rotation like that in the clockwise direction, then here the force required is not 4A by L. Because here it is 4A by L when other end is fixed. Because half that particular value will go there. But now here this other end is hinged, roller or simply supported. It is not able to take that. So here that value is different and that value is given by 3A by L. So stiffness of a member having one end fixed, other end hinged, roller or simply supported, it is called 3A by L. Whereas both ends fixed, we call it, or both ends continuous. Continuous also you can treat it as fixed only, right? Continuous and also like this. This is called continuous joint. There is more than one member is coming. It is continuous. Other members will share that, similar to fixed. Yet it will not allow to move. So it will take care about that force development. This is another factor. So another one more thing, we call it as relative stiffness. Here it is 4A by L, here it is 3A by L. Instead of using this 4, 3, E and all, simply we define the stiffness of this particular case as I by L, ratio between moment of inertia divided by length. That we call it the stiffness. Because any member, if you take, the geometrical property is known. That is B cross-sectional dimension, so E is known, Length is also known geometric property, so stiffness you can straight away take it as I by L. That's called relative stiffness when both ends are fixed. In this case, right, relative stiffness, it is 3/4 of I by L. 4A by instead of 4A by L, we take relative stiffness as I by L only. That means this we are dividing by 4E. So this also you divide by 4E. If I divide this by 4E, I will get 3/4 of I by L. So this particular member, 3/4 of I by L will be the stiffness. So remembering that either relative stiffness or actual stiffness, generally we go for relative stiffness because it is easier instead of having that figure 4E and all those things. Just I and L, it is just geometry, so we can work out the distribution factor. Here either stiffness or relative stiffness, either one we can use it. Both are same property. Here for distribution factors of OA is relative stiffness of OA, which is nothing but I1 by N1. Because for this member I have assumed I will be I1, L length will be L1. So this will be I1 by L1 divided by sum of relative stiffness of all other members. From all other members, what is the stiffness of this member, that proportion will be taken by that particular member. Here, relative stiffness of OA is I1 by L1 plus OB, it is I2 by L2, because there that member also one end is fixed, other continuous. This one end is continuous, similar to fixed, other is hinge. That is this case. Its relative stiffness is 3/4 of I3 by L3. 3/4 of I3 by L3. Right. Similarly, distribution factor of OB, if you want, that is I2 by L2 and this sum. Similarly, distribution factor of OC is 3/4 of I3 by L3 divided by this sum. So this is another important definition which you have to remember. That is distribution factor. Distribution factor, stiffness, carryover. So these three basic concepts along with fixed end moments. So each member has to be assumed fixed. Whatever member loading is there, due to that member loading, end joint moments you have to work out. Because in all our analysis, we assume all loads to be acting only at the joints. If at all loads are acting on the members, but in practice, loads will be on the members. We calculate the equivalent joint load. That is one fixed end moment. We assume the member ends to be fixed. Due to that, whatever reaction which are going to develop, we take it as fixed end. Why I am talking about moments only means because in the analysis we take moments only as the unknown. That's why we talk about only moments, not shear. Only if it is sway, then shear will come into picture. Otherwise, it is only moment. So next, that fixed end moment, another thing which you have to remember. Of course, already you know that in slope deflection method, we have used that fixed end moments. Why we have to find fixed end moment means during the analysis, all loads are assumed to act only at the joints. So, the possible type of loading or gravity type of loading only you have, one is UDL, W. Due to this, the equivalent joint moments which are going to develop will be WL squared by 12, WL squared by 12, because this is applied moment, resisting will be anti-clockwise, so it is minus. Another type of loading which you come across will be a central concentrated load which is acting on the member. then its equivalent joint moment will be W L by 8. This is W L by 8. This is minus, that is plus. Another type of load which generally you come across is eccentric concentrated load. This is called eccentric concentrated load. Concentrated load acting at a distance here from left hand, B from right hand, total length being L. In that case, the moment developed will be this end, it is W AB square by L square. Here it will be W BA square by L square. Then suppose you have a triangular load, this type of load, varying load, gravity load, varying from 0 at one end to W at right hand. In this case, if this is L, in this case here, where it is 0 to start with, the moment will be WL square by 30. Of course, it is minus, and this will be WL square by 20. Suppose if this varying load will be like this, right? Then it will be reversed. This side it will be WL square by 20, but anti-clockwise. This side clockwise, WL square by 30. Like that, you can have a moment also, all those loading cases. Generally, we get only this type of member loading. Suppose if you have a combination of all these, UDL as well as this, then you can split that into two cases, only UDL, only concentrated load. First, due to UDL, work of the moment, then concentrated load, work of the moment, add the two, that will be the resulting moment. That we call it as the fixed end moment due to loads acting on the members. So there will be another type of loading, that is settlement of support. That's also a type of loading in a given example that already we have worked a problem in slope deflection method. Suppose you get a settlement of a member like that. So the other two ends being fixed. There is a settlement here. So due to this settlement here, if this settlement is downwards, that is resulting in clockwise rotation, then the fixed end moment developed will be in the clockwise direction only, because it is positive. I told while working problems in slope deflection equation, it is positive, clockwise rotation only, and this moment it will be this force, it will be 12 EI delta by L cube. Here this will be 12 EI by delta by L cube, because here delta is the settlement. I have just now derived, due to unit settlement, force required is 12 EI by L cube. If there is a settlement of delta, it is 12 EI by L cube into delta. When that force is required here to cause this settlement, here there must be equal and opposite. These two will give you a clockwise moment, but this has to be equilibrium. It is stationary, so there must be an equal and opposite moment which will be in the anti-clockwise direction, like that. So this value, I told, it will be 6 EI delta by L square. There I have given 6 EI by L square due to unit displacement. Now displacement is delta, so this will be 6 EI delta by L square. This is the moment. Since it is anti-clockwise, it is negative. That in the slope deflection equation we have taken already negative equation for that delta. That's why I told you it is positive, don't change sign. Right? So this is the moment developed at the ends. So due to translation or this load, settlement of support in this member AB, there will be fixed end moment equal to 6a delta by L square. That you have to add it to the load, whatever is there coming. Due to loads, just now I gave, due to settlement, this is the fixed end moment which is going to develop. That you have to add it. So similarly for this member, it is anti-clockwise rotation, right here. So this instead of anti-clockwise, it will be clockwise. So you have to take plus 6a by L square. So that is the end moments developed on account of this settlement of support. If settlement problem is given, so this end moments calculated, fixed end moment, which is coming, which I told you now, that to be added to the load. Similarly, suppose if you have an overhang, then due to that overhang, whatever moment is coming, that is very simple. If overhang is W, load is W, L is that overhang, W, L is the moment. So here this will be the fixed end moment. That also you have to take. Whether in your problem, if there is an overhang or the settlement of support, already you know in slope deflection method you have got three problems. One only due to load, one only due to settlement, one only due to overhang. So you have worked out. Or all the three in one problem itself you can take and solve it. That's what let us do in moment distribution method. So this principle you have to, or basic definitions and principles you should remember before going for moment distribution method of analysis. One is stiffness, another carryover factor, another distribution factor, another fixed end moments due to various loads. Gravity load, settlement load, overhang load. If you know these basic principles, you can work any problem. And I will explain the procedure of doing this moment distribution with reference to an example using this basic idea. And of course, we have to satisfy equations of equilibrium and boundary conditions. What is the boundary conditions which are there at each joint? Along with that equilibrium condition, some of the moments has to be zero, that also to be satisfied. That we do in the form of table in the moment distribution method rather than using longhand computation as we did in slope deflection equation, writing the slope deflection equation, then applying equilibrium conditions, formation of equation, solution of equations. Those four steps, what we did in slope deflection equation, that will be replaced by a moment distribution table, with one table in moment distribution method. So in that aspect, this moment distribution method is simple when compared to slope deflection method. There, if you are consuming 4 pages, here it will be just 2 pages, exactly half the workload. That's the advantage of this moment distribution method, because all these equilibrium condition and also the stiffness, instead of writing slope deflection equation in that fashion, we take care in the table itself. Notionally we will do it and apply it, arrive at the values. Okay, now we will take an example.
Yes.